Okay, welcome back. We're going to look at some more examples involving conditional probability. Here we have a bag of M&Ms. This is a different bag than we were looking at earlier because it's got some plain and some peanut M&Ms of different colors, green, red, yellow, and brown. So for example, there's one green plain M&M, two green peanut M&Ms, two red plain M&Ms. And if you add some of these numbers together, you'll notice there's a total of 11 plain M&Ms and 9 peanut M&Ms in the bag. That's 20 in all. You'll also notice that altogether 3 of the M&Ms are green, there's 2 that are red, 5 are yellow, and 10 are brown. Again, the total is 20. What's the probability that an M&M chosen at random is yellow and peanut? Which ones fit that description? Those 3. There are 3 ways that we could have that be true. 3 ways that we could pull out an M&M that is yellow and peanut. That's if we get one of those 3 out of 20 in all. So that probability would be 3 over 20 or 0.15. Next question, what's the probability that an M&M chosen at random is peanut given that it is yellow? So when you see those words, given that it's yellow, you mean, okay, we're just looking at the yellow ones. If it's not yellow, we don't care about it. So we are given that it's a yellow M&M. It's one of those 5 yellow M&Ms. So if it's one of those 5, what's the probability that it's a peanut M&M? Well, that would be 3 out of those 5. 3 over 5 is 0.6. What's the probability that an M&M chosen at random is peanut given that it is red? So given that it's one of the red ones, the probability that it's peanut would be 0 out of those 2, or just 0. If it's red, it can't be peanut because there aren't any peanut M&Ms among the red ones. What's the probability that it is plain given that it is red? Well, that would be 2 out of 2, or just 1. Given that it's red, if we know it's one of the red ones, it must be plain because that's the only kind of red M&Ms there are. What's the probability that it is plain given that it is brown? So when you see given that it is brown, or if it's brown, or under the condition that it's brown, we know we're just focusing on the brown ones. If it's not brown, we don't care about it. But if it is brown, if it's one of those brown ones, what's the probability of it being plain? 6 out of those 10. So 6 over 10, or 0.6. What's the probability that it is brown given that it is plain? So now the condition is that it's one of the plain M&Ms, one of those 11. And in that case, the probability of it being brown, if it's one of those plain ones, is 6 out of those 11. 6 over 11, or 0.545. And returning to the book example from the last section, where we have some fiction, some nonfiction, some hardback, some paperback, some ebooks, what is the probability that a book selected at random will be fiction if it is an ebook? So if it's not an ebook, we don't care about it. But if it is an ebook, just focusing on the ebooks, if it's one of those, what's the probability that it's fiction? Well, that would be how many fiction out of how many ebooks? 40 out of 90. So 40 over 90 is about 0.444. What's the probability that it is an ebook if it is fiction? So if it's fiction, if it's one of the fiction books, just one of those. If it's not, we don't care about it. But if it's fiction, the probability of it being an ebook would be 40 out of 167. So 40 over 167 is 0.240 when you round to 3 places after the decimal point. Now remember, this is what multiplication rule 2 looked like. The probability of A and B equals the probability of A times the probability of B given A. Now, if I use my powers of algebra to take that equation and divide both sides by the probability of A, that rearranges it so that it says the probability of B given A equals the probability of A and B divided by the probability of A. And when you look at it from that perspective, when it's arranged like that, it becomes a formula for conditional probability, a rule you can use in certain situations where you're trying to answer a conditional probability kind of question. So in words, what this is saying is that the probability that B is true if A is true is equal to the probability that A and B both are true divided by the probability of the condition, A being true. So the probability of one thing being true if another thing is true is equal to the probability that they are both true at the same time divided by the probability of the condition, the given or the if part, being true in the first place. Here's an example. A website, imagine something like Amazon.com, sells both physical products that are shipped to the customer by mail and electronic content downloadable by the customer. So for example, you could order a physical book that would be shipped to you, or you can order an ebook that you could download and read on your phone or your e-reader. 80% of their customers purchase physical products. 20% of their customers purchase physical products and choose the super fast shipping option. What is the probability that a customer who orders physical products will choose super fast shipping? So let's break this down. When they tell us that 80% of the customers purchase physical products, you can interpret that in terms of probability as the probability of a customer purchasing physical products, being one of those, is 80% or 0.80. When it says 20% of their customers purchase physical products and choose the super fast shipping option, that's telling us that the probability of physical products and super fast shipping is 20%, 0.20. Now here's the question. What is the probability that a customer who orders physical products will choose super fast shipping? So it's asking, what's the probability that if this one thing is true, then under that condition, this other thing will be true? So the condition is that they order physical products. And in that case, given that that's true, we want the probability of this other thing being true. We want the probability that they choose super fast shipping if they order physical products. So the probability of one thing being true if something else is true is equal to the probability of both things being true, ordering physical products and choosing super fast shipping, divided by the probability of the condition, ordering physical products in the first place. And we know what both of those numbers are, so we just have to divide 0.20 divided by 0.80, and it comes out to 0.25. So that is the answer to the question, 0.25 or 25%. Now, I also told you we would be looking at least one questions. Questions that ask, what's the probability that you get at least one of something, or that something happens at least one time out of all the times it could happen? The key here is that at least one is the complement or opposite of none. It's either one or the other. Either none of the free throw attempts goes in, or at least one of them does. Either none of the coins comes up heads, or at least one does. Either none of the cards you pick is an ace, or at least one of them is an ace. Maybe more, but at least one. So those are complements of each other. And that means that the probability of at least one is equal to 1 minus the probability of none. And so that's often the easiest way of finding this probability. It's easier to find the probability that none of them are, that all of them are not. First one's not, and the second one's not, and so on. And then subtract that from 1 to get the probability that at least one is. For example, if you roll a pair of dice, what's the probability that at least one of them shows a 3? Now, we could just answer this directly. Go through and count out of the 36 possible outcomes, how many are there where this happened, where at least one of the dice shows a 3? Turns out there are 11 possibilities out of 36 in all, so the probability is 11 over 36, which is 0.306. But another way we could answer this is to go through and count the number of ways where none of them show a 3, where there's a 3 on neither one of the dice. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 ways that could happen. Notice that comes from 5 times 5. There are 5 ways that the first one could be not a 3. It could be a 1, 2, 4, 5, or 6. And there are 5 ways that the second one could be not a 3. It could be a 1, 2, 4, 5, or a 6. So the probability of both of them not being 3, probability that the first one's not a 3 and the second one's not a 3, would be 5 over 6 times 5 over 6, which is 25 over 36. And then that means that the probability that that's not what happens, that instead of neither one of them being a 3, at least one is a 3, would be 1 minus that probability. 1 minus 25 over 36 would be 11 over 36, or 0.306. Same thing we got as when we counted them directly. So that we could have done either way, but what if I ask you, if you roll 5 dice, what's the probability of at least one of them being a 3? If we tried to go through all the different ways that 5 dice could turn up and count how many of those outcomes have at least one of the dice showing a 3, it would take a long time because there are 7,776 possible outcomes. Not just 36, but 7,776 that we'd have to go through. So here it's definitely easier to go at it the back way and say that the probability that at least one of them is a 3 is equal to 1 minus the probability that none is a 3. That is, 1 minus the probability that all 5 dice are non-3s. That the first one is something other than a 3, and the second one's not a 3, and the third one, and the fourth one, and the fifth one. So that would be 5 over 6 times 5 over 6 times 5 over 6 times 5 over 6 times 5 over 6. And so what we really want is 1 minus that. That comes out to 1 minus 3,125 over 7,776, which is, well, in decimal form, 1 minus 0.402, which is 0.598. There's a 0.402 probability that none of the dice comes up showing 3. So there's a 0.598 probability that, no, that's not what happened. Instead, at least one of them, maybe more, maybe even all of them, but at least one of them was a 3. Okay, I'll be back with one more video with a few more examples.